Anna, are you going back to live stuff at Virginia? Live seminars?
Yeah, we have live seminars in
Okay.
UVA now.
Okay, good.
Okay, so good morning, good afternoon, everyone. So our speaker today is Anna Kuhn. Anna will be speaking on a note on the higher order Turan inequalities for K-regular partitions. Thank you, Anna, for joining us today, and the floor is yours.
Thank you. So this is the joint work with our first year graduate student in UVA. Now he's the second year student. So it is an interesting story because this is actually not my specialty. When I was in UVA, Chen was also like a new faculty member in UVA. So I took his course modular form because I want to learn more outside my specialty. And then I asked him what I can do, like is there any fun project that I can work on? And this is one of them. So, and then I realized that that's like a very fun project and you can use a lot of the method there to work on something else. So that's why I think that that's like would be a fun thing to share with everyone. So let me first start with just a definition. So a partition of a positive integer n, it's just a weakly decreasing sequence of positive integers whose sum of parts is just n. So for example, if I have n equals 5, okay, so like what are the possible partitions of 5? So I can have 5, I can have 4, 1, I can have 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1. So these are all the possible weakly decreasing sequence and of integers. And if you add them up, you get 5, right? So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 of them. And then you can actually define a partition function, which is just like giving me a number n. I just give you back the number of partitions of n. And then in like convention, we just write P0 equals 1. So for example, we just counted like P5 is actually 7, right? So this is like the partition function. And then another thing that I want to mention is log concave. So a sequence is called log concave, means that if you look at one term, square it, it's bigger than or equal to the product of the two terms right before and after it. So so that's am squared bigger than or equal to am minus 1 times am plus 1. So now there's a theorem. Like two groups of people were working on it, and then they used the different methods to prove the same statement. Is that the partition function Pn is log concave when n is big enough. So when n is bigger than or equal to 25, the partition function is actually giving you a log concave sequence. So what does that mean? So if you go to OEIS and then try to like look at all the like the partition function values. So for example, the first one here is the P0, and that's P1, and this is P2, P3, P4, and see, P5 is 7 here, right? So these are all the values of the Pn on the OEIS. And then if you go through all these, and then you realize that, say for example, if you use 3, you square it, you get 9. But then the number before and after you multiply them is 10. So 9 is not greater than 10. So the sequence, the whole sequence is not log concave when you are looking at the starting terms. But if you look further, say for example, somewhere like around here. So I think like starting from here, if you square it and then multiply these two guys, then the square is bigger. And then this pattern repeats. So like you can choose anything like this guy's square is actually bigger than the product of these two guys. So this is the meaning of log concave. So now it's a well-known fact that Pn is log concave for any n bigger than or equal to 25. So, oh, sorry. So then the founder of OEIS like asked this question is that, okay, well, how about other sequences? So he picked one sequence that he tested, and he said, okay, well, look at the sequence BM, and which is consisting of the partition of M, but this time he has one more condition, is that all the parts are distinct. Okay, so now that just means that BM is less than or equal to PM, because like you may not always get distinct parts. So now he claims that this is also log concave. Okay, so let's just like I have an example here. So for example, P5, I think I don't know why I have this one here. Let me just remove this. Okay, so let's just look at an example. Like when my n is 5, okay, or in this case, it's m is 5, and then we have 5, 4, 1, 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1. Okay, and then now we can think about what is our B5. Well, you have distinct part here, distinct part, distinct part. I don't want this because 1 and 1 are equal. These are equal, 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 right? So that just means that my B5 here is only 3. Okay, so now you can do this for any M. And then now, of course, you can go to OEIS again and look at the sequence and see, okay, well, is this sequence log concave? Ask exactly the same question. And so Sloane tried it to see the pattern and realized that, hey, like when you try it, it seems like it works when your M is big enough, but he does not know how to prove it yet. Okay, so he has this conjecture. So to tackle this conjecture, we can look at this sequence BM in a different way. So that's one of the keyword of the title of the talk, which is the K-regular partition. So what are they? If you first start with give me an integer k, which is bigger than or equal to 2, a K-regular partition of n is just a partition of n, of course, first of all. And secondly, is that no part is divisible by k. So that's the meaning of K-regular partition. So that's the definition. So for example, if I have the same n, which is 5, okay, and let's say if so look at just like all the possible partitions again. And then now say, for example, I choose my k equals 2. That just means that I don't want any parts to be divisible by 2. So what are the possible 2 regular partition of 5? So that would be my 5, 4, 1 is not good, 3, 2 is not good, 3, 1, 1 is good because that's no even numbers, right? And then this is not good, this is not good, and 1, 1, 1, 1, 1 is good. Okay, so this is when k equals 2. And you can ask, okay, how about the k equals 3? Then I don't want any parts to be divisible by 3. So I still have 5, 4, 1, 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1, right? So you can change your k. But if your k is too big, say, for example, I have my k to be 6, then of course, everything would work, right? Because there's no part equals to 6 at all, not thinking about divisible by 6, right? So now you can see that if your k is too big, then this sequence is actually going to be the same as the partition, like the Pn, the partition function. Okay, so that's K-regular partition. And now you may ask, okay, why do we care about this one? Because K-regular partition has a very close relation to what Sloane was asking about. So as before, as like partition, if you give me partition, I give you a partition function. Now I give you a K-regular partition function. I can also define a new function called the K-regular partition function, which is counting the number of K-regular partitions of n. So for example, we have n equals 5, and these are all the partitions. So we can see like P2 of 5 is 3 because of this one, and this one, right? And then we can have P3 of 5 is just the other. So we only count the one without parts divisible by 3. So we have these 5 of them, right? And then you can have P4 of 5. You don't want any part divisible by 4, and you see that that's only 6. P5 of 5 is 6 again. P6 of 5 is 7. P7 of 5 is 7. And any PK of 5 is actually 7, right? For all K bigger than 5. So this is a the partition K regular partition function. So what is the relationship between this and also the distinct part thing? Well, so, okay, so before that, I'm sorry, I forgot that I want to prove that, like how to count this, because as a combinatorics, you always want to know, okay, how do I know the number, right? Like if I give you an n, how am I going to give you back the pkn? So that's actually a generating function that we can compute, and that would actually help us to connect this to the distinct part partitions very soon. Okay, so how do we find a generating function? A generating function means that you use these values as the coefficients and then write a function out. So I have this pkn, and then you raise it to the power n, and now you want to know, okay, what is this function? Okay, so this is n bigger than or equal to 0. So now think about how do we count this, right? This k is fixed. So to make our life easier, let's just choose a easy k. So for example, I choose the k equals 3, so I don't want any parts to be divisible by 3. How do I make partitions of n? So the trick is you use the power to count stuff. So the first bracket here, I'm going to write these. So what am I counting here? These are counting the number of ones that I'm going to use. So number of ones, okay. And then the second one is the number of twos that I'm going to have. Okay, so this is the number of twos. I don't want any threes. And then I want some fours. And so on. And then you have all these. And so you may ask, okay, so for example, our n equals 5, right? We have 3 regular partitions, say 2, 1, 1, 1. It is a 3 regular partition. How am I going to form this, right? So that just means that I have 2, and then I have 3 ones. So when you multiply them together, you get x to the power 5, and that counts one of the x to the power 5. So it is like contributing 1 to this guy. So now if you multiply things together, you will see a lot of x to the power 5. So for example, you also see this, and this is x to the power 5. That just means that this corresponds to, you use 2 2s and 1 1, right? And when I count like this, you never see a 3 or a multiple of 3. So that's how you find the generating function. Okay, so once you have that, then we want to find a closed form. So let me just erase all these, make it easier to read. Okay. So we want to find a closed form for this guy. So to do that, we know this is just a geometric series. So this is like 1 over 1 minus x, 1 over 1 minus x squared, 1 over 1 minus x to the power 4, 1 minus x5, we don't want any 6, and so on and so forth. So what it means is that you have all these 1 minus x, 1 minus x squared, 1 minus x cubed, 1 minus x4, right? But you don't want, you want to delete the powers of 3, right? So that just means that is the product of 1 minus x3n over 1 minus xn, where n starts from any like 1, right? So that's the generating function. Okay, so that's good because now if you give me something like this, I can try to find the coefficient using different methods in analysis to find this P3n. So that's a closed form. So in general, if I just change this 3 to a k, if I change this to a k, then I can just change this to a k because the reasoning is exactly the same. So that gives us like a way to find all these pkn. It's not saying that it is easy, but at least we have like a closed form for this generating function. Okay, so now that's a theorem saying that pkn, that is the number of k regular partitions of n, is the same as saying the number of partitions of n with at most k minus 1 equal parts. So before I give you the proof, let's just verify this. So when n equals 5, k equals 3, P35 is 5 because we know that it's just like this, this, and this, right? So that's 5 here. And then we can count the number of partitions of 5 with at most 2 equal parts because k is 3, so 3 minus 1 is 2. So 2 equal parts. So let's see which one. So we have this one, still 2 equal parts, 2 equal parts, too many equal parts, too many equal parts, right? So there are 5 of them. Okay, so they both count as 5, but they are not the same. They're not the same set of partitions of 5. Okay, so that's a theorem saying that like you can actually count both of them and then you realize that they are the same thing. Okay, there's a combinatorial proof if k is 2, and they're like every circle combinatorial proof. But when k is larger, then I don't think I know any like combinatorial proof for proving the 2 things are equal. So the easiest proof that I know of is to use the generating function again. So how do we prove that? So we call that the generating function pkn xn that we just proved it is this n bigger than or equal to 1 minus xkn 1 over xn. So that's what we know. So now let's find the generating function for the other sequence. So let's say an is the number of partitions of n with at most k minus 1 equal parts. Okay. So now I want to find the generating function an xn. Okay. So how do I do that? Well, how do I form a partition with at most k minus 1 equal parts? So let's think about how many ones that I can get. I can have no ones, I can have 1 1, I can have 2 ones, but at most I can have k minus 1 ones, right? I cannot have too many. For the 2, I can have no 2, I can have 1 2, I can have 2 2s, but at most 2k minus 1, and so on. Okay, so now we can compute what these guys are, right? So again, it's a geometric series, so you can do this one is like, if you remember, geometric series is like a 1 minus rn over 1 minus r, so I'm using that. For all of them, the leading term a is just 1, so this is the formula. So I'm going to use this formula. So this one is 1 minus x to the power k over 1 minus x, right? And the other one is 1 minus x to the power 2k over 1 minus x squared, 1 minus x 3k, 1 minus x cubed, and so on and so forth. So now we have 1 minus xn, 1 minus xkn. Okay. So you can see that these 2 guys are equal. So they are formal power series, so the coefficients are also equal. So that's how you prove at least one way to show that the partitions of n with at most k minus 1 equal parts is actually pkn. So remember, the whole project starts with Sloane's conjecture, and he says that like the number of partitions of n with distinct part is log concave. So this is the sequence that we want to study. But with distinct part means that you have at most one equal part, right? So that just means that my k minus 1 is 1. So I want to write my 2, so that just means that k equals 2. So I can restate the conjecture and saying that actually Pm is just the P2 of M, right? Because that's the number of partitions with at most n minus, it's a 2 regular partition because my k is 2. So so now let's just write it in one line. Is that the Sloane conjecture is saying that P2M is log concave when your M is big enough. So that's the conjecture. So very similar to the partition function. And so now we may think about, okay, what are the to prove this, how am I going to prove this? And also, can we generalize this? Because this is kind of like a random thing to pick out one, like a k equals 2. So we may have like, can we have any k? Can I change the 2 to anything, right? Is that still true? That's one of the questions that you can ask. And then secondly is like, can we generalize the concept of log concavity? Why do I only look at log concave? Is there something more? And then also, what does that mean by sufficiently large? So how large means to be like large in love, right? So what is the minimal M that would make this work? So these are the questions that like we have in mind. And so now we want to get some inspiration from what we know from the partition function, and hopefully that would help us to solve this problem. So, okay, so how did people solve this problem? Okay, so they start with this statement. So they said the partition function Pn is log concave for all n bigger than or equal to 25, if and only if the following quadratic equation has only real roots for n bigger than or equal to 25. And let's see why they are related. So first of all, I start with that quadratic equation. So that quadratic equation means that this is like 2, 0, and then Pm plus 0, x to the power 0, 2, 1, Pm plus 1, x to the power 1, 2, 2, Pm plus 2, x to the power 2 has only real roots, right? But 2 choose 0 and 2 choose 2 are just 1, so I can erase those, okay? And then x to the power 0 is just x, and that's actually just Pn, okay? So if I rewrite it, this is just Pn plus 2Pm plus 1x, and then plus Pm plus 2x squared, okay? Has only real roots. Okay, so how do we do that? Well, quadratic equation, middle school stuff, we just look at the discriminant, right? So we have, this is if and only if 2Pm plus 1 square is bigger than or equal to 4 times Pn and Pn plus 2, right? So when you square it, that's the same as, and then both of them has a 4, so you divide both sides by 4. So you have Pm plus 1 square is bigger than or equal to Pn times Pm plus 2. So that's exactly log concave, right? Because you have Pm plus 1 square is bigger than or equal to the product of the term before and after you. So you can see that that just means that like even only if Pn is log concave, right? So that's how you link the log concavity and also this quadratic equation. So this is interesting now, because now I can just look at like a polynomial and see if there's any real root. So people start to learn about, okay, can I change a little bit? So now we change the 2 to a 3. So they again study the same thing. And they said, okay, well, if I don't care about log concavity yet, I just look at this polynomial, and then when would that be the minimal n that I can have real roots? Okay, so it is a very recent result. Is that in 2019, it says that this polynomial, just change the 2 to a 3, you get a cubic polynomial. This guy has only real roots when n is big enough, when n is bigger than or equal to 94. So now you may ask, okay, can I change the 3 to a 4, the 3 to a 5, and so on and so forth, right? And then actually, during the same year, it's also proved that by a group of people that for any d that you give me, the corresponding polynomial here has only real roots when your n is big enough. Okay. So now, what are these like big enough thing, right? So when d is 2, right, we know that is 25. When d is 3, which is this d3 here, we know that that's 94. And actually the same group of mathematicians, they also have a separate paper to tell you how to compute these NDs. So that's something that's very interesting, that you can have as a project to just look at all these ND. But this is like a very like kind of like an easy generalization. And it's kind of amazing that it only has real root when for any n when n is big enough. So now so now we see that all these guys have coefficient related to the partition function Pn, right? So now can we change this Pn to any sequence? Because we are looking at all these things so that we can work on the PK sequence, right? So we want to see if there's any result that is actually more general than only looking at the partition function. So now we have to like learn something new. So here, if I give you any sequence alpha of real numbers, the associated Jensen polynomial of degree d and shift n is defined by this formula. So so d and n are the expected number that you choose, and then it's very similar to what we have here. We just replaced the partition function to any sequence alpha. Okay, so this is the meaning of the corresponding Jensen polynomial. So for example, when our alpha is just our usual Pn, I should not use n because that's a little bit confusing. Pm, okay, so alpha m is our usual Pm, then our J alpha Dn x is just our J P Dn, so is this polynomial dj Pm plus j and then xj. So it is exactly what we saw before. Okay. So it's a more generalized, like a generalization of the polynomial that we were studying. So as we just proved that if our alpha is a p, right, and then we have this polynomial with this alpha is a p, and then we calculate that it only has real root if and only if this thing holds. But I never used the fact that that's like partition function. So the whole proof works if I just change it to any alpha. Okay, so that's good. That just means that the Jensen polynomial for any alpha has only real roots if and only if the alpha is going to be log concave. Right. So that's what we have. Alpha is log concave if and only if the corresponding Jensen polynomial is hyperbolic for n bigger than or equal to m. Hyperbolic is just a fancy name meaning that all roots are real. Okay, so I'm going to start using the word hyperbolic. Okay, so same thing. I can do it for the d change to 3, and then so the corresponding Jensen polynomial is hyperbolic, and then we have a polynomial, right? And then it's a cubic thing, so you can compute the discriminant and then try to find like a nice condition on the coefficients. So it is not straightforward, but it's already in the literature, and it's known that the corresponding Jensen polynomial is hyperbolic if it satisfies all these three inequalities. Good. So now how about if I have a bigger D? I have D equals 2 and D equals 3. How about all these, right? So that comes to the second keyword of the title of the talk, which is like Turan inequalities. And sometimes people call it Newton inequalities. So what are these things? First of all, you give me any degree R polynomial with real coefficients. So because it's degree R, so AR is non-zero. And then a degree R polynomial has R roots. Okay, so I call it beta 1 up to beta R be all the roots of fx. Some of them may be complex, right? As we don't know yet. So we can define something called Newton's sum. So S0 is just R, and Sm is just the sum of the nth powers of your roots. Okay, and I cannot include the m equals 0 here because if all the roots are non-zero, that's fine. But if one of them is 0, then 0 to the power 0 doesn't make sense. So that's the reason why I treat S0 separately. But it's kind of the same as treating it as the same formula. Okay. All right. So these are called Newton's sums. Now I can define a matrix. So the Henkel matrix of all these S0, S1, S2, and so on and so forth. So I'm going to give you an R by R matrix where R is the degree of your original polynomial. So this is your matrix. So it's very easy to write. So you start with S0 and then go there so that the size is R. And then the next one you start with S1 and go on. And then you can see like a pattern that this is S0, S1, S2, S3, right? So you can form a matrix like that. So in 1863, so this is in 1863, Hermite has a theorem saying that if you give me any degree R polynomial with real coefficients, then f only has real roots. That means f is hyperbolic, if and only if the corresponding matrix is positive definite. So how do we know if a matrix is positive definite? Well, you just look at the principal minors, right? So you just compute the these principal submatrix and compute the determinant, and you want all of them to be positive. Okay. So what it means is that I want this guy to be positive, and this is a gift. This is always true. And then you also want this guy to be positive. So you want this inequality to hold. You also want to have this bigger one has like a determinant bigger than 0, and so on and so forth, up to the last guy has to be bigger than 0. Okay, so that's the theorem. If you give me any degree R polynomial, if you want to know if it is hyperbolic, you just form a matrix and check the determinant. Okay, so now that just means that f is hyperbolic if and only if delta 1, delta 2 up to delta R are all positive. And that means you have to have R inequalities in SI to be satisfied in order to claim that f is hyperbolic. But remember, these guys are just the sum of powers of the roots. So they are all like the S1, S2 up to any S sub R is actually, S sub K is actually like, you can express it in terms of the coefficients of your F, right? So for example, the product, the sum of roots is like, you have this like, this divided by this and so on and so forth. Oh, sorry, this divided by this and so on and so forth. So this is like the product of roots, right? So you can do like simple calculation to express SM in terms of the coefficients of F. So that just means that all these like delta 1 to delta R are inequalities in the coefficients of F. So that's good. So now if you give me an alpha, which is a sequence of real numbers, so before that, I should just clarify what I'm trying to say is that if you give me any polynomial in degree R, then I want to say that it's hyperbolic if and only if there are R inequalities in the coefficients of F are satisfied. Okay, so like checking hyperbolicity is just checking R inequalities, a set of R inequalities. Okay, so now why did we learn all these stuff? Because we start with something like I want to study a sequence, right? And then we know that like at least for the Pn situation, they find the associate Jensen polynomial and they prove it by proving the associate Jensen polynomial is hyperbolic. So that's why we want to know how to check something is hyperbolic. Okay, so get back to any sequence. Now, if I apply the Hermite polynomial on the Jensen polynomial, then that just means that the corresponding matrix has to be positive definite, right? And that gives us a set of inequalities on the coefficient of this Jensen polynomial. And these inequalities are therefore in these coefficients, right? And these coefficients are depending on the alpha that you chose. That is the sequence, right? So that just means that the corresponding Jensen polynomial is hyperbolic if and only if all those inequalities in terms of your alphas are satisfied. Okay, so we call this set of inequalities the order D Turan inequality. So that's the order D Turan inequalities comes in. And it's a little bit different is that the order D Turan inequalities also include the equality case. Okay, so what does that like? What do they help us, right? So what is the statement? So if you give me any sequence alpha, I form a corresponding associated Jensen polynomial. I want to check if it is hyperbolic. So it's the same as saying that the corresponding delta 1 up to delta D are bigger than 0. Delta D is because like it's a degree D polynomial and because that's the degree of your Jensen polynomial. Okay. So if you are all positive, then of course you are bigger than or equal to 0. So the Jensen polynomial is hyperbolic implies that you are satisfying all these order D Turan inequalities. Okay. All right. So conclusion is saying that the Jensen polynomial is hyperbolic implies all these deltas are bigger than or equal to 0. The first two is the order 2 Turan inequalities. Those three of them gives you an order 3 Turan inequalities up to the last, up to like order D inequalities, you all satisfy. So what it means is that if you have a Jensen polynomial is hyperbolic, if and only if your alpha is going to satisfy all these order 2, order 3, order 4, up to order D Turan inequalities. So for example, now get back to how they prove it. You give me an alpha, and then I choose the alpha to be partition function. That just means that alpha m equals PM. Then the corresponding Jensen polynomial is what we just like calculated, right? So it is this quadratic equation. And this quadratic equation, you can compute the S0, S1, and S2, okay? So S0 is just 2 because that's the degree. S1 is the sum of roots. So you have minus B over A, right? And then and then S2 is the like the sum of the square of the roots. So we know that if alpha and beta are the roots, then you have alpha plus beta to the square minus 2 alpha beta. So you use those to compute S2. Okay. So that just means that delta 1 is 2. Delta 2 is the 2 by 2 determinant, and I calculated it for you. And then, and you only need 2 because like it is the 2 by 2 matrix, right? The Hankel matrix is the D by D matrix. Now my D is 2. So the Jensen polynomial is hyperbolic if and only if delta 1 and delta 2 are bigger than 0. Delta 1 is of course bigger than 0, and delta 2 is bigger than 0 if and only if this guy is positive, right? So that gives you the reason why the Pn satisfy the order 2 Turan inequalities, and that's the same as saying log concavity. Okay. All right. So conclusion here is that if D is 2, I can prove that the Jensen polynomial is hyperbolic for n is bigger than or equal to 25. That's the same as saying Pn satisfy the order 2 Turan inequalities when n is bigger than or equal to 25. When D is 3, then the Jensen polynomial is hyperbolic when n is bigger than or equal to 94. So when n is bigger than or equal to 94, Pn satisfy the order 2 and order 3 Turan inequalities. And if you remember, that's like the most general result is saying that the Jensen polynomial corresponding to the partition function is hyperbolic for big enough n. So that just means that if you give me an n, if it's big enough, then Pn satisfies order 2, order 3 up to order d Turan inequalities. So now get back to our 3 questions. So we still don't know if PKM is log concave or not. But at least we already generalized the meaning of log concavity because now we use the Turan inequalities to generalize log concavity. Log concavity is just saying that it's satisfying order 2 Turan inequalities, but I can have order 3, order 4, order 5, and so on and so forth. So that's a generalization of log concavity. Okay, so at least we answered the 1 question. So how about if I'm just looking at PKM instead of PM, right? So how do we do that? So so if I write it down, it's like a statement, it's saying that, okay, well, if I change the P to PK, is this corresponding Jensen polynomial hyperbolic or not, right? Because I want to see if it is satisfying the Turan inequalities. If I can prove that the corresponding Jensen polynomial is hyperbolic, then I'm all set. So, and also if this is true, then I just pick K and D equals 2. That's exactly what Sloane conjecture was asking about. So if I can prove that, then the Sloane conjecture would hold. Okay, so this is just telling you why, because like P2 is what we want, and then we only need degree 2 because log concavity. Okay. So now, what is the idea? So the idea is that, okay, I want to say the Jensen polynomial is hyperbolic. That's what I want to prove. So is there something out there that I already know is hyperbolic? And if I can say that the Jensen polynomial is that polynomial, then I'm done, right? So that's the best scenario. If I already know that the Jensen polynomial is something that we already knew in the literature, then I'm done. So now we go back to the literature and see if there's anything that can help us to link the Jensen polynomial and it, and also hopefully that thing is hyperbolic. So that's the idea. Okay, so, and actually we are lucky. We can actually find something like this. So how do you find that? Well, first of all, I fix a D, and that's the Hermite polynomial that helps us. So the Hermite polynomial is defined by the exponential generating function of e to the power minus t squared plus xt. Okay, so you may ask, okay, so what's x1, x2, x3, and so on? So we know how to expand this, right? Like this is just like how I think Cal2. So then you just expand it, right? And then you have this 1 plus xt, x squared minus t squared over 2, and so on and so forth is like a Taylor series expansion. And then now you just compare coordinates. So x0 is this 1 because it's t to the power 0. And then x1 is just x, x2 is just x squared over x squared minus 2, x3 is just x cubed minus xx. Okay, you take the coefficients of the t to that power, and that will give you like a bunch of polynomials. And I'm claiming that these polynomials are all hyperbolic. Okay, so this is a well-known fact, and we can actually track that. So for example, x1, you only have 1 root, which is 0. x2, the root is square root of 2 and plus or minus sign. x3, the roots are 0 or plus or minus square root of 6, right? So all of them are real roots. So if we can connect our corresponding Jensen polynomial with this guy, that would be great. So then, actually in the same paper, they have a way for us to check. I know it's super technical here, but the point is, you just look at the last line that we want. give me any alpha, I can prove that the Jensen polynomial is the corresponding Jensen polynomial is hyperbolic for large enough n. If like you can find some other kind of like a sidekick and then satisfy like this equation. Okay, so it's just checking thing and try to come up with the other two sequences. So if you can do that, then you can say that I normalized it, so that's just like with some scalar multiple, differ by some scalar multiple from your original Jensen polynomial, so it's not going to change the fact that your root is real. And so this normalized guy is actually the Hermit polynomial, which is known to be hyperbolic. So this would be hyperbolic as well. So if we can find that, that's great. So that's very exciting. So we were like, okay, well, how are we going to find this an and delta n? So so like we tried to look at some clues in the literature, and actually in 1971, Higgins was studying this function pkn, and it gives us a very good asymptotic formula for pkn. And that gives us some clue of how to find this an and also the delta n sequence and satisfying this blue line here, okay? Of course, I'm not going to show you the proof here, but at least I want to let you know that we are just looking at this answer and get some idea of how to construct the an and delta n, and then now we can use the theorem, okay? So, and this is the answer. We realized that like we do some math and then we realized that we can just pick these two choices for the sequence and then we check the conditions and it works. And yay, then we have a theorem. And because then that just means that by the previous theorem, like the very technical one, we can prove that the normalized Jensen polynomial is actually a non-hyperbolic polynomial. Great. So, and that's an easy corollary and saying that the corresponding Jensen polynomial is hyperbolic for big enough n. So in particular, if we just choose the d equals 2 so that it's log concavity and also k equals 2, then that proves Sloane's conjecture. Okay. And of course, you may ask, okay, well, what are these big enough, right? That's the third question. What are big enough n? So we wrote a program to generate all these numbers, and there are lots of things that we can explore, but we didn't do much on this one, and we move on to another project. But there are lots of things that if you're interested, you can explore. So for example, we know that like pkn is actually pn when your k is very big, because like say for example n is 5, you don't want any parts to be divisible by 6. It's just no condition at all, right? Because that's impossible to have any part divisible by 6 when you're a partition of 5. So when your k is large enough, everything is just going to be the same as what we know for pn. So that just means that if you fix a d, and then when your k is large enough, it's the same as the nd for the partition function. So this one is for the partition function, this one is for the k regular partition function. So that just means that if you look at all these, that would gives us the n2, which is the original 25, n3 is the original 96, n4 is like 206, and so on and so forth. And of course, you can look at these sides as well. So there are lots of things that you can explore. You can think about, can we find like a way to find this NKD, and what are the properties of this NKD, and so on. So so this NKD actually grows like ND. So there are lots of things that you can explore here. And for the last part that I want to talk about is that why are these things important? Okay, so why do we study Turan inequalities, or why is that like very technical theorem is important? One of the reasons is that like that paper with that technical theorem there is actually studying something for the Riemann hypothesis. So it is known that the Riemann hypothesis holds if the Riemann C function is in the Laguerre-Polya class. And so we want, of course, we want this to hold. And so we want to check this, right? So then a necessary condition for the Riemann C function to be in this class is actually, if you give me this function, I look at the Taylor series expansion as n is 0, look at their coefficient, they all satisfy the order R Turan inequalities for any R, then this is like then you can, so that is the necessary condition for the Riemann C function to be in the class. So if any of them fail, then that just means that the Riemann hypothesis would not be true, right? So, so the Riemann hypothesis is the same as, and also the other thing is that the Riemann hypothesis is the same as looking at the Jensen polynomial for the theta function at the point of symmetry. It's the same as checking if it is hyperbolic. Okay, so that paper in 2019 by Chen and other mathematicians are actually proved that the hyperbolicity for this case, but for large enough n, not for all n. So it is not proving the Riemann hypothesis, of course not yet, but it gives you some insight. But as a combinatorics, what you can actually take away from these things is that this theorem is very general because I just changed the alpha to pk. You can actually use this alpha to any other sequences that you are interested in and try to see if there's any pattern that you want to study. And this method should still work for any alpha, like any sequence that you are interested in. So, so this is the end of my talk, and thank you for listening.
Thank you, Anna. So yeah, thank you. Thank you. Let's see if there are any questions from the audience. And really enjoyed your talk. So let's see.
Thank you.
Yeah, your talk was beautifully presented, Anna, and beautifully written.
Thank you. Thank you.
Yeah, and it's interesting to see the connections with, you know, the different areas, you know, it's like, yeah. So you mentioned you are not working on this project anymore, yeah? So working on.
Yeah, so like I worked out on something else, which is something related to T-hooks, which is also like in number theory. And I worked out on something with the circle method. So to find like that's like something very interesting in the T-hook part, like a partition function, but it's not just K regular partition. And then find a closed form for it using circle method. And then from there, there's something very interesting phenomenon that we didn't expect because it's something related to even and odd. And you would think that when n is very large, then everything is like evenly distributed, and it appears to be not. So like we didn't know why, and then we tried to actually find the find the exact formula for that function and then see why that happened. So that is another very interesting topic that we we worked on with this grad student as well.
Thank you. Okay, any questions? Let's see in the chat box. Okay. Well, let's thank the speaker again.
Thank you.